Hello. Today we're going to dive into the world of pressure, which is a crucial concept in physics. We'll learn the definition and formula for pressure, look at how it works in real-life examples, and even talk about how we can prove the direction of the force it creates.
Hi, pressure sounds interesting. I've heard the word before, but I'm not really sure what it means in physics. Where should we start?
We should start by thinking about why a sharp nail goes into wood more easily than a blunt one, even if you hit both with the same hammer force. This difference shows that the effect a force creates depends not just on the strength of the force, but also on the size of the area it pushes against.
Oh, okay. So it's about how concentrated the force is? Like, the same force is spread out over a bigger area on the blunt nail, making it less effective?
Exactly. You've hit on the core idea. We quantify this concentrated effect using a ratio we call pressure. Pressure is simply defined as the force acting on a surface divided by the area over which that force is spread. How would you write that as a simple mathematical formula?
So if pressure is force divided by area, would it be P equals F over A?
That is precisely correct. We write it as P equals F/A. In science, we use specific units. If the force, F, is measured in newtons, N, and the area A is measured in square meters, M squared, the pressure P is measured in a unit called the Pascal, PA.
Okay, so P is in pascals, F is in newtons, and A is in square meters. So if I push down on a small button with 10 newtons of force, and the button has an area of 0.001 square meters, what would the pressure be?
That's a great application of the formula. The pressure would be 10 divided by 0.001, which is 10,000 pascals. This shows that a small force can create a very large pressure if the area is tiny, which brings us back to our nail example.
Wow, that's a huge pressure from only 10 newtons. So thinking about the formula, P equals F/A, does that mean if I double the force, I double the pressure, assuming the area stays the same?
Yes, that's absolutely right. Since force is on the top of the fraction, increasing the force increases the pressure proportionally. Now, let's look at an example to apply this idea in a real-world scenario.
Sounds good. What kind of example are we going to look at?
Imagine a heavy box that weighs 24 newtons. It is 3 meters long, 2 meters wide, and 4 meters high. If you place this box on the floor, the pressure it creates will change depending on which side it rests on. Why do you think that is?
Well, the force is always the weight, 24 newtons, no matter which side it's resting on. But the area it's pushing down on changes. If it rests on the smallest side, the area is smaller, so the pressure will be bigger, according to P equals F/A.
Excellent deduction. The weight, force, stays 24N, but the base area changes. Let's calculate the pressure if the box is resting on its largest base, which is 4 meters by 3 meters. What would that pressure be?
Okay. The area is 4 meters times 3 meters, so that's 12 square meters. The force is 24 newtons. So the pressure would be 24 divided by 12, which is 2 pascals. Is that right?
That is perfectly correct. The pressure is 2 pascals. Now let's see what happens if we put the box on its smallest base, which is 3 meters by 2 meters. What would the pressure be in that position?
Let's see. The smallest base is 3 meters by 2 meters, so the area is 6 square meters. The force is still 24 newtons, so 24 newtons divided by 6 square meters gives a pressure of 4 pascals. That's twice the pressure.
That is a clear demonstration of how decreasing the area increases the pressure, even with the same force. We've finished discussing the definition and formula for pressure. Before we move on, can you quickly state the formula for pressure and the unit we use for it?
The formula for pressure is P equals F over A, where P is pressure, F is force, and A is area. The unit for pressure is the Pascal, or PA.
Fantastic. Now that we understand the math, let's move to our next objective, looking at more real-life examples where changing the area or the force affects pressure. We already talked about the nail, but think about someone walking in soft snow. Why is it easier for them to wear skis instead of just boots?
I guess it's like the box example. When they wear boots, their weight is on a small area, so the pressure is really high and they sink into the snow. Skis have a much bigger area, so the pressure is lower, and they can stay on top of the snow. Is that why?
That's the perfect explanation. Wearing skis spreads the person's weight over a greater area, which significantly reduces the pressure. This is a great example of reducing pressure by increasing the area. We see the opposite effect with nails, which are pointed to reduce the area and thus increase the pressure so they can penetrate surfaces easily.
So anytime you need to cut or pierce something, you want a small area to create high pressure. Like a knife blade is very thin. And anytime you need to support something, you want a big area to reduce the pressure. Like wide foundations on buildings, is that a good way to summarize those two uses?
That's a brilliant, concise summary. You have captured the main application of pressure mechanics perfectly. Now that we've seen how pressure changes with area and force, let's move on to our final objective, describing an experiment that shows the direction of the force produced by pressure.
Okay, I haven't really thought about the direction of the force. When I push a box, I push it down. But does pressure always act straight down?
That's a key question. To figure out the direction, imagine you are blowing air into a balloon. The pressure of the air inside the balloon is higher than the air outside, which is why the balloon inflates. But why does it inflate uniformly outward, and not just in one particular spot?
Because the air molecules inside are hitting the rubber everywhere? So the pressure is pushing equally in all directions against the inner surface of the balloon?
Exactly. The uniform inflation shows that the air pressure inside acts in all directions equally. Now, if we imagine dividing the balloon's surface into many tiny spots, the force at each spot is always pushing straight out. This proves that the force produced by pressure is always acting at a right angle, or perpendicular to the surface it is acting upon.
So it doesn't matter what shape the container is, the force from the pressure is always pushing out perpendicular to the surface at every point? Like if the container was curved, the force would follow the curve?
Yes, that is a perfect way to visualize it. If the container is curved, the pressure force at any point is always 90 degrees to that curved surface, like a ray shooting straight out from the spot it touches. We can apply this idea to liquids too. Liquids cannot be compressed. You can't squeeze their volume down, and they pass on any pressure applied to them throughout the liquid.
Oh, so if I push down on the top of a container of water, that pressure gets transmitted throughout all the water, and it pushes on the sides and the bottom with that same perpendicular force?
Precisely. This principle, that liquids transmit pressure, is used in devices like a hydraulic jack. Imagine a hydraulic jack used to lift a heavy car. A small downward force, let's call it F, is applied to a small piston with area A. What formula represents the pressure transmitted through the liquid?
The pressure would be the small force divided by the small area, so P equals F/A. Since the liquid transmits pressure, that same pressure P is pushing on the larger piston, right?
That is absolutely correct. The pressure P equals F/A is transmitted uniformly. Now that same pressure P acts on a much larger piston, which has a big area, A. We want to find the large load, F, that this bigger piston can lift. Since P equals F/A, how would you rearrange the formula to find the load F?
If P equals F over A, then to find F, I need to multiply P by A. So F equals P times A.
Excellent. Now, if we substitute the pressure from the small piston, which was P equals F/A, into that second formula, F equals P times A, what would the final equation be for the load F? This combined formula shows how a small force can lift a very heavy load.
F equals F/A times A. So the large force F is the small force F multiplied by the ratio of the big area A to the small area A. That means if the big area is 10 times bigger than the small area, the output force is 10 times bigger than the input force.
That is a perfect final formula and a fantastic insight into the power of hydraulics. It shows exactly how a small effort can be magnified to lift a large load simply by using a larger piston area. We have now covered the definition and formula for pressure, its real-life applications, and the direction of the force it creates.
That was a great lesson. I feel like I understand pressure much better now. It's not just about the force, but how that force is distributed. Thank you.
You are very welcome. You showed a great understanding of how force and area interact to determine pressure. Thanks for taking the time to join me today. You did great. Have a fantastic day.